Okay, page 11. Okay, so it's given the region enclosed by natural log of x minus 3, the line y equals 7 minus 1/4 x, and the x-axis. Sorry, I forgot to provide the instruction here to find the area, of the enclosed region. Okay, so I'm gonna explore using top minus bottom first, since everything's already in that form. So, but the problem is that, well, let's say I want to draw one representative rectangle and imagining it stacking from one end to the other. We see that there's going to be an issue, right? Once we get past this intersection, the top function is going to change. And so we can't rely on just one integral to for a top minus bottom. We need a second one because the top function is going to swap. It's going to change relationships with a different graph. So we'll do top minus bottom twice, but that would require us to know where that is going to change, and as well as for us to know where the starting and ending points are. So we're going to use our calculator to help us find that. So go to our calculator, we'll plug in these functions. So y1, natural log of x minus 3. Seven minus 1/4 x. If you do alpha trace, sorry, alpha y equal, you get that n over d. Math print. Okay, I'll do zoom 6. Get that standard window. It may not be perfect, but at least it kind of gives me a starting point for me to graph. And so it's all the way to the right here. I don't have to look at all of this space right here in negatives. And I'm going to probably stretch out to 50 just so I can make sure that I can see everything. So x min, x max looks like I can adjust that. Maybe I just start from -1. Just picking, I just know that anything to the left is not going to, left of the y-axis is not really going to be helpful. Let me go to 50 here just to see what I can see here. Okay, so I didn't have to go that far, but this is good enough for me to get a good idea where I need my two x-intercepts here and I need my intersection. Okay. All right, so let me start off with second trace. Let me start with zeros here. I'm going to start from the left and go to the right. So I'm going to pick a point. I'm going to find the x-intercept. Hit enter. Pick a point to the right of the x-intercept, hit enter. It's going to find that x-intercept for me. So 4. Second trace intersects. I want to find the intersections of my two graphs. So I'll pick a point on the curve, pick a point on the line. I'm going to write both those, the full order pair. Right now, though, I only need the x. Second trace, I'll find my x-intercept again, 0. I'm going to pick a point to the left of the x-intercept, pick a point to the right of the x-intercept. 28. Okay, so everything I need is in front of me now. Now I can do top minus bottom twice. Once for this side of the intersection and then another for the other side of the intersection. I'll just do a dotted line here to indicate that I do need two separate integrals here because there's a change after that dotted line. So furthest left, x value to the furthest right of my first region. Okay, sure. Okay, so top minus bottom here. So the top is this natural log of x minus 3 minus, what's the bottom of the rectangle touching? X. What's the equation of that line? 0. Y equals 0, yeah. So minus 0, yeah. I really didn't need that 0, but I want to just make sure that we're following the rules here and we're seeing all the different parts here. Top of the rectangle is on the curve. Bottom of the rectangle is sitting on the x-axis, which is 0. Top minus bottom. Okay. Here the line is now going to be the top function. So the 7 minus 1/4 x. But let's do the integral from okay, so we practice in our calculators here. So we can do math 9 from 4 to 17, and then math 9 again, 17 to 28. Any questions here? Now this is perfectly fine, doing top minus bottom. We can also do right minus left. Area is one of those problems where you can decide whether, sometimes you can do it both ways, either top minus bottom or right minus left. I know most students are going to prefer to do top minus bottom, which is fine. I'm going to show right minus left though, just so that we can kind of get that practice with converting our bounds and our equations. So I'm going to attempt this problem using right minus left. But on the quiz, if you have a choice and you just want to choose to do top minus bottom, that's fine. But for us, I just want us to get that practice. Okay, if we know that if we want to do right minus left, if we want to draw a horizontal rectangle, our equations have to be rewritten in a different form. So the line initially was 7 minus 1/4 x. We have to spend the time to solve for x. So I'm going to just add and subtract in a way where I'm going to move that 1/4 x to the left, move the y to the right, multiply by 4, eventually solve for x. If I multiply everything through by 4, I can get rid of that 1/4 x. Distribute that 4 through. Okay, so now this 28 minus 4y is the rewritten form of this line here. Okay, let's work on the curve. Y equals natural log of x minus 3. I want to put that natural log of x minus 3 on the left side. I want to solve for x. To solve for x, I want to get rid of this natural log. To get rid of the natural log, I can do what on both sides? Yeah, raise both sides. E is the base. E and natural log are inverses of each other. They're going to cancel each other out. X minus 3 equals e to the y. Solve for x. Okay, so we'll do right minus left. The nice thing about right minus left in this case is that there is no change in relationship, right? No matter where we shift this rectangle up and down this region, this right endpoint of every rectangle is touching the same graph every time, and the left endpoint is always touching the other graph. There's no sudden change like what we see here with top minus bottom. So all we need is one integral. But everything's in terms of y, so our bounds are also in terms of y. So what are our bounds going to be? Lowest is 0. Highest is
2.6.
Yeah, 2.66. There you go. Okay. So right minus left. The right endpoint of my rectangle is on this orange graph, which is the 28 minus 4y. Minus the left endpoint of my rectangle is sitting on the green graph, which is the e to the y plus 3. Make sure you put a parentheses around that. Practice plugging this in your calculator. Use x's wherever you see another variable. We should also get 39.052. Questions? All right, number 2, we have a shaded region here. You got the natural log of x plus 6. You got the y equals -3. You got the x equals 5. Now, the X and Y axes are not boundaries. Some students feel like they have to split this up because of the X and Y axis. They're just in the background. They're just for us to kind of have a uh, frame of reference. And AP exams, they do that as well. Sometimes when they draw the graph, they like to draw that X and Y axis to help us see where the graph is. Okay, so there's our shaded region. Find the volume of the solid generated when the enclosed region is revolved about the line y equals -4. So this is y equals -3, so y equals -4 is going to be below that. Anytime we see the word revolving, we know it's going to be either washer or disk, because that rotation, that 360-degree rotation, is going to cause that circular shape to come out. So it's either disk or washer. But here's y equals -4, clearly below the shaded region. Okay, disk or washer method. Washer method, yeah. Now, if this line was up at y equals 3, -3, then that will be this method, right? See, up against a flat surface, there's no gaps. Here, there is a gap, so washer method. Our axis is horizontal. Our radius is always going to extend out from that dotted line. So it's, in this case, my radius is going to be vertical. So from the dotted line, we're going to extend to the furthest boundary. That's going to be our big R. Okay. From the axis, extend to the closer boundary. That's going to be your little r. Okay. Build big R and little r. Big R, top of big radius, is sitting on the curve, the natural log x plus 6. Minus the bottom of big radius is sitting on the dotted line. The dotted line is y equals -3. Oops, sorry, -4, my bad. The bottom of this line is -3, but this is y equals -4. Okay, little radius, top minus bottom. The top of little radius is sitting on the -3. The bottom is sitting at the -4, so we subtract them. So -3 minus a -4. Little radius will just be a 1. Okay, we do need to go to the calculator to find the furthest left x value, and then we know the furthest right is going to be x equals 5, because that's what that vertical line is. Just have to figure out what this intersection is. So I'm going to go to my calculator here. Okay, so natural log of x plus 6 and the line y equals -3. That's what I'm trying to figure out that intersection of. Zoom 6. I'm going to zoom in that region there. It's kind of hard. I mean, the reason why it looks like it's disappearing is because there's a vertical asymptote there. So it's kind of disappearing into that asymptote. But I mean, technically, it goes all the way down. It doesn't just stop there. It's just the asymptote is so close to it. It's we're not seeing it. So I'm going to do zoom box, zoom 1. I'm going to go to that intersection there, or at least zoom in on that intersection there. So I'm going to create a box around that region. Pick an upper right corner. Okay, so that's better. Now I can pick points on either side, or pick the two graphs, and actually I didn't have to do that. I could have just do intersect without zooming in, but I think it's good practice for us to kind of zoom in. Pick points on two graphs and ask the calculator to find our intersection, negative 5.95. Okay, so our volume is pi. Now we're washer method here, so pi is going to show up. Definite integral from furthest left to furthest right, so negative 5.95 to x equals 5. That's the equation of this vertical line. Big radius squared minus little radius squared. Practice in your calculator here, 320.510. And don't forget, add pi. We can insert this under y1, insert this under y2. F9. Let me know if you have any calculator questions or issues plugging in or getting that answer. Okay, next page. Okay, next page, same shader region. But let's see, we're now revolving about the line x equals 5. So that's, we know it's going to be either disk or washer. We know to see the word revolving, there's rotation. But here is my axis of revolution right at this boundary here. Data region. All right, so disk or washer method. Yes. Disk. Yep, there's no gap anymore, right? If it was on this side and if it was touching, we see there's still all that gap there, right? So just because the graph is touching doesn't mean that it's this method. This will not be this method either if the line was up here. So it's got to be up against a flat surface where you don't see any gaps at all. That will be this method. Okay, so only one radius is needed. We extend from the axis to the furthest boundary. All we need is one radius. All right, we see a horizontal radius, so what adjustment do we have to make? We got to rewrite our equations, right? So this one is already x equals 5, so this one is okay. But we have to rewrite equations of that line. Sorry, of that curve. So that equation is natural log of x plus 6 equals y. Going to have to work towards solving for x. So we see natural log that's in the way. To get rid of that natural log, I'll raise both sides. E is the base. Okay, one radius, big R. Right minus left. Right endpoint of my big radius is sitting on the x equals 5, so that's going to come first. 5 minus left endpoint of my big radius sitting on the e to the y minus 6. Careful though, big parentheses. because anything that follows a minus has to be distributed. Okay, so any questions so far? All right, so volume equals pi depth integral. Now we need to find the lowest and highest y values here. What's the lowest y value? -3, because that's the easiest spot. The highest y value is going to be the y value at this ordered pair, right? Now, this ordered pair, we know the x value is 5. How do you think we can find the y value?
Plugging it in.
Yeah, plug into the original function, right? Because with this curve, if I give it the x value, I can just go ahead and find the y value. We don't have to, and we're not gonna be able to do this in the calculator because the calculator is not gonna allow us to graph a vertical line. But I mean, we can just use what knowledge we have, right? Just plug 5 into the function, get that y value, get that location of that order pair on the curve. So if I plug 5 in for x, natural log of 5 plus 6, that's equal to what? Natural log of
1.
yeah. So that's the y value. All we need is one big radius squared. Right, plug that in the calculator. Okay, questions so far? Okay, next up, number 3, we have f of x equals root x plus 6. X plus 6 is the that concave down graph, the one on top. The e to the x plus 1, that's the exponential function. That's going to be the one that's below, but kind of has that, it's going to rise as the graph moves to the right. And the x and y axis are just there as background. It's not going to be a part of any of our boundaries. Find the volume of the solid generated when the enclosed region is revolved about the line x equals -6. So this is my axis of revolution. X equals -6, that's a vertical line. Okay. Anytime there's a rotation, we know it's either disk or washer method. In this case, which one would it be?
Washer.
Washer. Yeah, so we need 2 radius, right? One that is an extent from the dotted line to our furthest boundary. And then little radius will start on the dotted line and extend to the closer boundary. All right, anytime we see a horizontal radius, we know we have to spend the time to rewrite our equations. So this curve was e to the x plus 1. We have to get that in terms of x. Okay, I'm going to isolate this e to the x first. So I'm going to subtract 1. I want to solve for x, but x is stuck in the exponent. What can we do to allow that x to come down? Take the natural log. Yeah, natural log has a nice property which allows exponents to freely move. That x comes down in front. We know natural log of e is just going to be 1, so that's going to go away nicely. So x equals natural log of y minus 1. That is the rewritten equation of that curve. Okay. Now the square root function, I'm going to have to rewrite that one as well. Root x plus 6 equals y. I'm going to solve for x. So to solve for x, I want to get rid of that radical first. I can raise both sides to the power of 2. I can square both sides. X equals y squared minus 6. Okay, everything that we need is in front of us. We do have to use our calculators to find those intersections. We need the y values. Let's go ahead and write both the x and y values because I think we're going to need the x values later. Okay, I'll do zoom 6. I'm going to do zoom box in that region there. Makes it easier for me to do intersection. Zoom 1. Upper corner, hit enter. Okay. Second trace intersect. I'll do the intersection of the left intersection first. And negative 4.986 and 1.006. Okay, second intersection, second trace, intersect. Point 429 and 2.536. Okay, we didn't need X values order pair right now, but I'm going to just go ahead and write them down so we use them later. Next problem, we don't have to type all that in again. Okay, so two radius is needed. We have two big R's, or two radius, two for washer method. Okay, big radius. Right endpoint is sitting on the orange curve here, that being natural log of y minus 1. Left endpoint is sitting on the dotted line, which is -6. Okay, small radius, right minus left, right endpoint of small radius sitting on the green curve, the y squared minus 6. So y squared minus 6 minus a -6. The -6 and +6 cancels out. I'm just left with the y squared. So big R, little r. I have my bounds, lowest to highest y value. Okay, my lowest y value is 1.006. My highest y value is 2.536. Right, everything's in terms of y. So my bounds also have to be in terms of y. Okay, practice entering in your calculator. Okay, two more to go. Page 13. Okay, so it's the same shaded region as before. You got the square root of x plus 6 on the graph on top. You got the e to the x plus 1. That's the exponential on the one below. The enclosed region is the base of a solid. The cross section, okay, so this is a cross section problem here. Taken parallel to the y-axis is an isosceles right triangle with hypotenuse on the base. Find the volume of the given solid. So first things first, we have to identify which direction do we want to build our base. Is it vertical or horizontal? They tell us parallel to the y-axis. Which direction is that? Vertical. Y-axis is vertical to begin with. Parallel to it, that means we want to have that same direction as the y-axis. So vertical. No rotation going on here. This is not a physical washer method. Imagine this as a flat surface that sits on desk, and we're trying to build these shapes that's going to come out of the page. And let's build that base length, and then we can worry about the shape. The base is going to be top minus bottom, just like how we would do area here. So what's the top of my base length sitting on? Root x. Minus, bottom is sitting on the exponential. Careful, parentheses. We need the bounds in terms, well, sorry, let's do the bounds later. Let's build the area first. So the area, we talked about yesterday, how we want to be able to memorize these formulas here. So We want an isosceles right triangle with hypotenuse on the base. The formula are pretty much all base squared. Just have to worry about the coefficient. What's the coefficient for hypotenuse on the base? You guys remember? 1/4. Yeah. So just a quick reminder here. Square is base squared. Isosceles right triangle is 1/2 base squared. Isosceles right triangle with hypotenuse on the base is 1/4 base squared. The difference here is that it's either leg on the base or hypotenuse on the base. That's going to change the orientation of the area there. Rectangle is base times height. Equilateral triangle is √3/4 base squared. Semicircle is pi/8 base squared. This is also in the back of your quiz review, so that hopefully you can get that under our belt before we take our quiz. Okay, so 1/4 base squared. Okay, so we have our base length, so I'm going to replace this into the formula, right? And have that as my base. So if that's my area, then really the only thing that needs to be done to get to the volume is that we just bookend our area with our integral notation, right? The integral on the left, the dx on the right, and then hard part is just get to the area. Once you get to the area, then you're just doing notation to get to build that volume extension there. So this one, we're going to go from the furthest left to furthest right. So that the order pair that we pulled off of the calculator can come in useful because we're going to now need that x value. So the furthest left the graph is going to be is -4.986. The furthest right is 0.429. Plug all this in the calculator. There is no pi in front. There's no rotation. There's no circle related anything here. But it's still units cubed. It's still volume. Okay, one last one here. We have -x² plus 4, the -1/2 x plus 2, the -x² plus 4, that's the parabola that opens down because of the negative. So that's the parabola. You got the linear graph here, -1/2 x plus 2 with a negative slope. Find the volume of the solid generated when the enclosed region is revolved. So we see that revolving there. We know it's either disk or washer method. Along the line y equals 4. So y equals 4 is going to actually skim the surface of that parabola there. Okay. Disk or washer method? Which one is it? Washer. Yeah, it's touching, but there's all this gap, right? There's no flat surface for this dotted line to go up against. So there's no chance this shape can ever be disk method. This can only support washer method. Okay, I draw two radius, one that extends to the curve, another one that extends to the line. So here's my big R. Here's my little r. I have vertical radius, which means that top minus bottom is what I want to use. The nice thing about top minus bottom is we can use these equations the way they give us. There's no need to rewrite anything. Right, we'll build our radius. We have to graph this so we can find the intersections, the X value intersections. Okay, top minus bottom. The top of big R is sitting at the 4 minus big parentheses. And the bottom of big radius is sitting on the linear graph, the -1/2 x plus 2. Do some cleanup here. Okay, little radius, top minus bottom. The top of little r is sitting at the 4. Bottom of little r is sitting on the parabola, the -x² plus 4. Fours cancel out. I'm just left with x squared. Okay, we need the bounds, so let's go to our calculator, find those intersection points. Second trace intersects. Pick points close to the left intersection here. All I need is the x value, so -1.186. Pick a point closer to the right intersection there, 1.686. Okay, put everything together here with washer method. Big radius squared minus little radius squared. Okay, and the calculator goes, we get 10.268 pi meters cubed. Okay, let me know if you have any questions. If you have a what?
What do you? That's wrong.
Oh, let's see, your question again?
When you go on something, don't put.
You don't, right? Well, the one exception with cross section is semicircle.
Okay.
That pi over 8, but yeah, it's either pi over 8 with cross section or diff and walker. That's the only time you use pi. There's no other pi we got pi. Yeah, X equals. Yeah. If you see it, if you see a horizontal, radius, then you have to rewrite it.
Yeah, I just ignore the
Ignore in terms of, after you rewrite it, then you can ignore it. It's not gonna come right. But sometimes that original equation can help you find bounds,
That's what, okay.
right? But in terms of actually using it in the volume formula, you're not gonna use the original.
What she was talking about, the priority extension, is it okay if we plug pi into the calculator then, or do you still want us to keep those separate?
I'll accept either form.
Okay.
Yeah.
When you're doing like cross section of a rectangle, how do you find height?
They will describe the height.
Okay.
The height will be either like a number like 5 or 6. Or they would say the height is 1/2 the length of the base.
Okay.
Then you just have to figure out what that base is. If the base was like x, then that will be your height, and then your base will be x plus 1. It'll be base times height, and that will be the area of your rectangle.
That makes sense.
Bye.